So first, I'm very glad to be here. In fact, some 3 or 4 years ago, I defended my PhD in the room next to here, so that's a bit less impressive today, but still, I'm really happy to be there. So we're going to speak about compilation of Python program. But first, let me introduce the whole team. So we are all here. There are 2 of us. So me, Serge, I'm working as a R&D engineer in a security society, Quarks Lab. So this has really nothing to do with Python. You would be surprised to see how I can use Python in security, but that's nothing with this talk. And I'm also an associate researcher at Télécom Bretagne. It's the same engineering school as here, but in Brittany. And Pierrick used to be one of my students, but I managed to keep him under my umbrella, and now he's working at the INRIA as a R&D engineer on parallelism, and we are both spending some of our free time on this project. So Pythran in a nutshell. When you write scientific kernels, some 40 years ago, you write it in Fortran, and it was doing all you wanted. And the idea of this compiler is to say that the kind of Python program you write for numerical computation, in fact, it's Fortran. You don't know it, but it really looks like Fortran. In fact, with my compiler guy eyes, when I look at this code, it really looks like Fortran. So I don't understand how a compiler So I don't understand how a compiler can't make it run as fast as it used to for Fortran code, because it really looks the same. There are a bit of syntactic sugar inside, but it looks the same. So we have to support everything, and it should be possible. So what is Pythran? It's a compiler from Fortran-like, but written in Python code, Numpy-centric, and it translates it not in Fortran, but in C++, and then normal C++ compiler turns it into efficient code. So it's not only a translator. I mean, it's a source-to-source compiler, but not only translate one line of Python to one line in C++ and expect it would work faster. The goal is not to write C code. C code is not fast. You can't write fast code, but if you translate Python code to C code, it's not enough. What we want to do is also to optimize the Python code at the Python level. So we take the Python code, we generate new Python code, we turn it into C++, and then it runs faster. When you do this, if you want to support real-world scientific code, you need to support NumPy arrays, but also NumPy functions. And so we had to implement this function into C++ so that they can execute efficiently. So we have a wrapper library that implements part of the Python built-ins, that implements part of NumPy library and some other libraries. So that's what we rely on. So the core concept, because you've been hearing about Python compiler for a few years. I mean, there is Cython, there is Numba, there is parakeet, there is Hope, so there are plenty of them. So what makes us different? I think that the main difference is that we are focusing on high-level code. When you look at the code that scientific writes, there's a lot of NumPy function. There's no that much explicit loops. So we don't want to turn this high-level code into loops by hand. We want to compile them. So that's the first concept, high-level code as input. And then we don't want to generate assembly code, right? We want to generate high-level code because it's easier, and then all the low-level stuff, register allocation stuff, and so on, it's not done by us, it's done by another compiler. So we generate high-level code from high-level code, but first we perform optimization. We will list a few optimization later, and then we want performance. And as I said, performance is it's not only a matter of generating statically typed C or C++ code. It's a matter of using the hardware. And what kind of hardware do you have? I see a lot of Apple stuff here, but there's also an Intel processor, I mean, everywhere. So you all have multi-cores. You all have SCMD processor in your Intel processor. So you have to use this if you want your code to run fast on your laptop. And it will run fast on workstation too. So we want to use it, we want to take advantage of the parallelism in your laptop. And then we want to be reliable, so we test, and we test again. To give you an example, for every test case we have in our validation suite, we run it on inputs in Python, and then we collect the results, then we compile it with Pythran, we get a native library, we run this library on the very same input, and we need the exact same output. So that's the kind of correctness we want, just the same output, the same behavior as NumPy. Even when NumPy doesn't respect the standard, in terms of each other standard, we just do the same. And then we want to bench, because if we want to go fast, we have to measure how fast we go, so we bench a lot. So that's the core concept. And then when you do benchmarking, you need test case. How do you get test case? There are 3 ways of getting test cases. The first one is to use Mandelbrot, because you know that's a very easy kernel to compile. It's not memory bound at all, so you will get very great speed up, because writing a naive Mandelbrot in NumPy is really, really slow, so it will be really great to advertise for your product. So we don't want to do this. The other solution is to write your own kernel, because you have some kind of scientific background. I don't understand anything about scikit-learn, but I have some scientific background, so I can write a dot product, and I say, oh, I want my dot product to go fast. But that's very biased. I mean, I am writing the kernels for my compiler. I know what my compiler supports and what it doesn't support, so that's unfair. So the other way is to ask some people. And where do you ask things? You ask things on the internet. You ask Stack Overflow. So you just go on Stack Overflow and you type, oh, NumPy is slow, how can I do? And then you get a lot of questions. People come with their codes, so that's real codes, because that's not mine, that's real people. And at the beginning, on the question, the code is slow, and in the answer, the code is fast. So you get the way people optimize their code. So that's the kind of code we get. Based on my assumptions, this looks natural to you. You are using NumPy, initializing an array, extended slices, using NumPy random, huge computation, a few loops, but a lot of implicit loops here. So that was his code, and he thought that was the way to get fast computation in NumPy. So if I summarize, whoa, my code is slow. So I tried to use Cython or Numba. So I just added a decorator, or used the type annotation from Cython, and then it compiles, but, well, it's still not very fast. Why? What is the answer? The answer is you have to make all your loop explicit, and then these tools will be able to optimize your code and to run them faster. And it runs faster, of course. So that's the Cython version. Not written by me, just taken from Stack Overflow. You have a lot of cdef, it looks okay. And then, whoa, it looks okay, cdef, woo! Oh, I'm really glad that 40 years have passed, because this looks like Fortran to me. So I'm back to writing Fortran instead of writing high-level NumPy code. But that works and gets faster, so why should I worry? In Pythran, you just take the original code. You add this single type annotation here to say what are the type of the inputs, not the type of each of your variable, but the type of the inputs. And then that's all. You call the compiler, and it works. So that's a bit of effort compared to a JIT annotation. But what do you get? If you benchmark the original code, you get something like 50 milliseconds from time it. If you call Cython, compile the code, benchmark again, something like 35 milliseconds, so it runs faster, it's okay. And then you compile it with Pythran, you enable, that's just the flag forwarded to the C++ compiler, and it runs around 20 milliseconds. So what do I take? The lesson I learned is that, to the opposite of the common Python knowledge, explicit is not always better than implicit. If I make my loop explicit, it will not always help the compiler. How to say this? I think that to write efficient loops, that works better than a compiler, you need a PhD. I've been studying this for 3 years, and a bit more after that, and now I think I can manage to generate loops that goes as fast as what a polyhedral compiler can generate. But my guess is that scientific guys don't know how to write loops. No, so that's okay. There's a timeout, or he needs to take breath or whatever. So you don't want to write the loop on your own. In fact, nobody here is writing assembly anymore. So you're writing C. So why would you want to write loop? If you're in Python, you need abstraction. So forget about explicit loops. Then the optimization hints. In Cython, you can say, don't do any bound checking on this. You can, or parallelize this loop, or this kind of thing. A compiler can infer this information from your code. It counts any time, but most of the time, it can do it. So let's try to do it. And when you're using high-level constructs, there is a semantic behind. When you're using a vector operation in a Numpy, you know how it's done, so you can express this in terms of this is a parallel construct or this is a vector construct, and you can use the semantic to generate better code. Once you have your loop, the semantic is gone away. So keep the high-level code and give it to a compiler that understands it. So I really don't want any problem with the Cython guy. I just checked. There are something like 1,000 stars on GitHub on Cython and 200 stars on Python on GitHub. So they are right and we are wrong. Okay, why? Because they are pragmatic. They are in the real world. We are just two, we are dreaming and we are idealistic. So we're just trying something else. Okay, so they are right because what they are doing is working for everybody. So that's a good way to go. We have the right to dream. So why is it difficult? Why did they choose to be explicit? It's difficult because these 3 lines of code are taken from the same kernel, and there's a lot of things to do here because there is an extended slice, and the semantic of extended slice is quite complex. There are broadcasting here, there are some NumPy functions, and so if you want to compile everything here into native code, there is a lot of work to do. So what they are saying is, whoa, that sounds difficult. What we want to do is translating, so the user will do the difficult part. There is also a problem with aliasing, because some variables are starting to share some pieces, some memory area. So when you're writing to a variable, you're also writing to another variable, and that's the kind of stuff that are difficult in compilation, so they just don't care about this. Then there are a lot of optimization opportunities. There's nothing new in this slide. You may know of the numexpr package. That's exactly a good candidate for numexpr, but here, NumPy is not doing very well because it's creating a lot of intermediary arrays. There are some variables that are not useful. They can be forward substituted. The loop behind this could be merged into a single loop. It could be made vectorized, it could be made parallel, and all these optimization opportunities have to be used if you want to generate efficient code. And one way to do this is to use Pythran. So as every compiler, the man page is very complex because you have a lot of flags, but basically you call the compiler on an input Python code and it turns it into a native module. And then you can forward all flags to GCC if you want to customize your stuff. So a few examples. The first one, you just take your input.py and give it to Pythran and generate a .so, and you can load it as a regular module. You can also have a look to the generated C++ code using a -big E, which looks like a preprocessor flag. If you want to bleed from your eyes, that's a good way to start. You can also ask for OpenMP code generation, then you add the typical OpenMP flag. And if you don't care about mathematical accuracy, you can use the big O fast flag, which does what it does in GCC, but just faster mathematical evaluation to the price of less accuracy. So that's not the default in Pythran, to the opposite of another compiler, which I will not give the name. We try to be accurate, but if you know that you can't be accurate, you have the control. There's nothing magic. You can't turn polymorphic code into C++ native code without types. As we are a static compiler, the type information must come statically. And so we have this kind of annotation. We are not annotating every function. You only annotate the function you are going to import in another module. So that's the exported functions. So you can just give the name of the function and then the type of the parameters. If your function can accept is really polymorphic, which means that it can accept several kind of parameters, it's supported too, and we support end array, tuple, list, well, the things you're supposed to need. Then there is a difficult slide, technical slide, so I bravely give the mic to.
Okay. Thank you, Serge. I will present the Pythran internal parts, what we are doing in it. So if you look at this diagram, it's just like what you see in your compilation lessons when you were at course. There is a front end, so we just turn the Python program to an abstract syntax tree, which is a classical representation for programs. Then there is a middle end. We just perform optimizations and create an internal representation of every programs. And finally, we dump a C++ file, which is then compiled to be imported in Python. So for the front end, we totally rely on the AEST module from Python, which do also our job from us. It performs parsing and creates the abstract syntax tree. It also checks the functionality we are supporting, because with Pythran we try to support every fun part of the Python language. So we support polymorphic functions, many types for the most commons, multiple dimensional array type, because name parameters are really a good way to write function calls and to know what we say, we support it. It's the same for default arguments. Generators are really funny to compute everything lazily, so we support it. But there are some parts that are not supported, like global variables. Many Python modules are not supported, but if you want to create a push request for us, you're welcome on our GitHub. And we don't support user-defined classes, but well, Pythran is just like Fortran. Fortran doesn't support classes. We don't need to support classes. It's just the same. About the middle end, here is a list of multiple optimization we are doing, but I will not just present all of them because it's tedious for me and for you. So the most important are constant foldings. So constant foldings is when we detect that a function have no side effects, that it is pure, we can evaluate its value if the input value is constant. For example, if you write a Fibonacci function and you give 5 for inputs, then we will compute it at compile time and replace the function call by its value. We do some other stuff like removing temporal variable. For example, to forward a constant everywhere in the program to make it easier to optimize later. And we try to compute lazily some intrinsic functions, just like map, range, filter, and some others, because sometimes you just want to iterate through all of these value, and you don't want to create the full list from the original values. And finally, the backend. So for the backend, we have two backends. We have a Python backend because well, when we have a bug, we don't want to read C++ code. It's not really easy to read. Python is really better for it, so we just dump the Python code equivalent to the C++ ones, so that we can see what we are doing and how does it work. I'm sure the same for you. You don't want to read C++ code. And but we have to generate C++ code sometimes for the real Python modules. So we call the C++ library called Pythonic that Serge explained before. Thanks to this generation, we can create lazy evaluation through expression templates. So when you have complex NumPy expressions, you don't want to create all the temporaries. So you will compute everything in a row, and it will be really faster. And as Serge said, we want to benefit from our recent architectures with parallelization and vectorization. So for the parallelization, we rely on OpenMP, and for the vectorizations on BoostSMD, thanks to Joel, who did a really great work on it. And all of this is done automatically on the NumPy computation. Typing. It's weird to speak about typing with Python because it is really dynamic compared to C++, but we have to care about it, and to make it as polymorphic as possible, we create template functions and instantiate them to create a polymorphic code. But well, it's just complicated, and when you read typed polymorphic code into C++ metaprogram templates, it's just like fun, but complicated. About parallelism, as I said, there are implicit parallelism with OpenMP and BoostSMD for NumPy array expressions, but you can also give some explicit parallelism to the program thanks to OpenMP-like annotation for those who already write this kind of code. Here, with numerical, you say that everything in the loop can be done in parallel, so you can benefit from the multi-core you have on your machine. So Serge will continue with engineering stuff.
So a last part of the talk about benchmarking. So we have been collecting benchmarks for our own purpose. The goal is not to have a suite for, benchmark suite for everybody. The goal is just to be able to reproduce our benchmark, so it's a good job for us, but it's also a good job for you. So it's everything on GitHub, right? The code has been gathered from Stack Overflow, and we also picked some benchmarks from the other compiler suites, so we are very fair. And most of these codes are high-level codes, so there is not that much loops. The goal is to see which part of the NumPy API is used a lot and how you can optimize them. There are all the dirty stuff to benchmark this code on CPython, PyPy, Numba, Parakeet, Hope, and Pythran, even if it's not very fair to compare to them because the goal is different, but still that gives an idea. So the only purpose of this slide is to say, whoa, so that's a logarithmic scale. When the green bars are very high, it means that there were loops inside, so NumPy was very slow, so Pythran was able to take advantage of this to go very fast, but it's not really Pythran that is great, it's just that the original code was very bad. And on the other cases, you get a factor of 2 or a factor of 3 compared to the original NumPy code, and that's already a good achievement. And in fact, that's we are really trying to be fair in the sense that there is no vectorization applied here, no parallelization applied here. So the bar would go higher with all switched on, but that just gives an idea of the kind of performance you can get. Then there is code that is written using loops. So look at this code we've been taking from the Numba blog. There is functions and then loops, loops, and loops, loops, loops. It's very loopy. So that's the kind of code you may want to optimize to. So that's not because we focus on high-level code that we don't support low-level code. It's just that, for example, there will be no vectorization here because everything is explicit and we don't try to get the information back. In fact, the backend compiler may try to do this, but it will be difficult. So we don't help him. But, well, so what we get here, again, NumPy is slow. So everything that can translate it reasonably fast in native code will go very fast. We are a bit slower than Numba here, but that's already great. I'm not very fair with SciPy here, so if there is any SciPy developer here, I really apologize. But my SciPy version should be a bit too old. But the idea is just to say that you can compile this kind of code with Python and it goes reasonably fast too. Another way to compare or to benchmark is to write papers. So if you're in academia and you like quoting other paper or reading a lot of paper instead of watching TV in the night, well, you have something here. A last part, it's not very nice for ourselves to talk about this just now, but we are only two of us. There is no full-time engineer there. It's on our family time. So we are trying to do the best we can on engineering there. For example, we have, well, the digits are not fully correct. I think that we have around 3,000 test cases that are run each time we do a pull request. Everything runs on Travis. To give you an idea, our full validation is validating with or without SCMD, with or without OpenMP, and it takes something like 6 hours on the Travis integration stuff, because we don't have a premium account, to have all this running. So well, it's for free, so it's okay. It's peer-reviewed code, so we can't do like scikit-learn because we have only 2%, so there can't be 3 other people looking at the code, but I can't commit without the acknowledge of Pierrick and so on. So we are trying to reviewing. If Jan Oswald is here, we are still waiting for your pull request for Python 3 supports. And it's C++11 inside, so we are mostly working on Linux. We have heard of stories of people managing to make Python work on OS X. There's a few stuff to do, but it's almost okay. And there is an internship for a guy trying to port this to Windows, a bit more work, but it's ongoing, and the guy looks very good, so it should be okay. If you like reading documentation, there's plenty of it for you. You can have to look to GitHub on PyP, and there is a lot of native dependencies. So if you're not comfortable with installing Boost and this kind of thing, you just add my custom Debian repository and fetch everything on your Ubuntu, and it should be okay. We need more peons because there is a lot of work to be done still, because, well, the C++11 part is not as clean as it could be. It's okay for the Python part, but C++ part is not as clean, yes. So we need a serious cleanup, so anyone fan of C++11 can help here. The typing part is very funny, but I don't have a PhD in typing, and I should have one to do it in the proper way. So help here is welcome too. If you want to improve your favorite OS support, it's okay. We already received a pull request for Arch Linux support, but if you have a strange distribution, feel free. And we are starting to support numpy.random and numpy.linalg. Not reinventing the wheel, but just writing the wrappers with the C++ standard library or with OpenBLAS. But still, if you like wrapping stuff together, which I adopt, you can be helpful here. So that's the end of the talk. Several students from Telecom Bretagne have been working on the project. Some of them willingly, the others are not longer here to speak about this. But thanks a lot to them. Even if we are too open source, very small, we managed to get industrial support thanks to a very great charisma. So thanks to Silkan and to Numscale for their support, either in terms of working force or in Finnish support. And there's a lot of bank here, or assurance, or anything. So come to talk with us afterwards. If you want to contribute, free node, free lists, GitHub, no Twitter. Thanks.